Hello everyone, and welcome to this webinar from Precision Polymer Engineering and Global Spec, and thanks for joining. In this webinar, I'll talk about the plasma resistance of elastomer parts and try to explain how the purity of an elastomer material affects the semiconductor processes. The presentation will be focusing more on dry processing applications and the effects of various process chemistries on a variety of different elastomer materials. Before I start, I'd like to introduce myself and my background. My name is Murat Gulkur, and I'm the Global Product Manager for Precision Polymer Engineering's Semiconductor Products and Materials. I started to work in PPE in early 2015 as a senior scientist in R&D department, developing new materials for semiconductor applications, and then moved to product management role beginning of this year. Before joining PPE, I worked in Leeds and Durham universities, leading industrial and academic research projects on single molecule electronics and printed organic semiconductors. I also worked in elastomer industry for a couple of years before that. I am an organic chemist having a strong understanding of almost all semiconductor processes for chip manufacturing. Okay, this is a brief overview of the topics I will discuss today. There will be a quick introduction to PPE, just in case you haven't heard about us before today. In order to help non-elastomer experts more about the elastomer technology, very basically, I will talk about the simple elastomer formulation and some basics about elastomers. Then we have some plasma exposure data of elastomeric materials in various different chemistries, and we will see which types of materials might perform better or worse in which applications. And finally, I have a couple of slides on what I've called purity, and this is describing and comparing the trace metal levels of some common elastomer materials. Okay, I'll start with a brief overview of Precision Polymer Engineering, or PPE for short. PPE is a manufacturer of high-performance elastomer parts for critical high-value applications. We've been around for over 40 years, and we are focusing on market sectors such as oil and gas, industrial, and semiconductor industry. We are based in Blackburn, which is in the northwest of England, where we have about 75,000 square feet facility for production, and we have various accreditations for manufacturing processes and quality, etc. PPE is a part of IDEX Corporation, and we are part of much larger organization. And IDEX Group has total annual revenues of over $2.5 billion US dollars. So what does that mean? So this gives PPE and our customers certain advantages, including the financial security that comes with being a part of much larger diversified group, and provides a certain stability of supply to our customers. As you can see by these two images on the slide, the investment has recently been put to good use through an expansion of our facility in Blackburn to another manufacturing site in Brenham in Texas in the US, which is now up and running and currently serving mainly semiconductor customers in the US and other regions around Americas. Both these sites specialize in compression molding and for critical semiconductor products. The parts are being made in clean room conditions, so there's minimum contamination for the products manufactured both in Blackburn and Brenham. We also acquired another company 2 years ago based in Italy called Novatima, who also produce elastomer products, but they concentrate on much higher volume applications with custom injection molding capability. This is the overview of the types of products we make. Vast majority of the products we make are O-rings. We are capable of making O-rings from very small diameters to very large, up to 2.6 meters. We can also make other shapes like D seals, X seals, D seals, or other shapes like gaskets or small other molded parts. We are also capable of making very small parts by our special injection molding capability with very small tolerances. For semiconductor industry, one example to this is end effector pads for robotics applications. We are also capable of making bonded elastomers, like gate valve door products. We can mold and bond elastomer materials into gates for use as spare parts in exchange in vacuum door valves. Many of our materials are recommended by OEMs, and we can also supply monowatt gates with PPE elastomer materials. In the previous slide, I talked about our products. Now, these are our material families used in semiconductor applications. Well, most of you may know Perlast is our very well-known trade name for years, which covers all the fully fluorinated or perfluorinated FFKM materials. Kimura material family is a range of fully organic fluoroelastomers where particle contamination and plasma resistance are concerned. Nanofluor is a range of hybrid materials providing high purity which demand extreme plasma resistance. So any other materials made by PPE are sold under PPE trade name, for example FKM materials for semiconductor applications. Okay. Obviously, there are some very strict requirements to supply parts to semiconductor industry. One of the most important requirement is the cleanliness of the parts. In order to satisfy this, in PPE, we have dedicated cleanroom facilities to prepare the elastomer formulation and to do all the other process steps to make the final elastomer part in our clean rooms. I have a dedicated slide to talk about this more in detail later in this presentation. The second key requirement is to have low trace metal content in the elastomer material. So the trace metal contamination can cause some electrical faults in the semiconductor processes, and in PPE we have a very good track record of having ultra pure materials such as Perlast G67P, which is one of the cleanest FFKM material in the market. Obviously, having all the processes in the clean rooms of rubber part manufacturing helps maintaining the purity. Additionally, in our formulations, we always use very pure ingredients, very pure polymers to maintain the trace metal contamination at the lowest possible levels. We also work very closely with our suppliers to provide us always the cleanest ingredients. And finally, an elastomer part used in a semiconductor application must not generate any particles during its service life. As I mentioned earlier, our polymers are designed and engineered to minimize particulation. Also, PPE's 40 years of expertise in high-performance rubber compounding is also a key to maintain minimum particulation. This is because an elastomer material which is not compounded, prepared properly, can cause particulation during the service. I have a very good example of this later in this presentation, comparing the scanning electron microscope images of the competitor materials versus PPE materials. Okay, now we come to the fundamentals of elastomer compounding. In PPE material portfolio for semiconductor applications, we have lots of different materials for different applications, and we try to keep all these formulations as simple as possible to maintain the purity of the elastomer. So anything added extra into the formulations means a higher chance of contamination. Therefore, we want to keep all of our formulations as simple as possible. Obviously, we need to have a polymer in an elastomer formulation, which is the main ingredient of all elastomer formulations. When we need to have a curative, essentially to join polymers together, and that bit is fixed. The curative chemistry will be matched to the specific polymer being used, and there's a certain set of process conditions needed to make this chemical reaction to happen for a set time, and we have some options then. So this polymer curative pair is the main part of a formulation. The properties like elasticity, minimum maximum temperature capabilities, chemical resistance, mechanical properties, and radical plasma resistance, actually, which is chemical resistance of a polymer, are all determined by the type of the polymer. So for a basic pure elastomer formulation, we do not need to add anything else on this. Just polymer and curative will work. But we have another optional ingredient, which is the filler. And in some cases we need to mix or compound in various types of fillers to fine-tune the properties of the elastomer materials, such as hardness, tensile strength, etc. But where stiffness, dimensional stability, reinforcement, and generic plasma resistance are needed from the elastomer material, fillers are also being used. Now, when an elastomer is used in an aggressive plasma environment, there's the potential for these filler particles to be released as the material, the polymer erodes in whatever chemistry it's used in. So you can pick a material that will be very clean and have no filler, but it will erode a lot faster rate than a material that might have much lower erosion rate, but the lower erosion rate material can have the higher potential to create particles. So you can't have everything in one, but you can try to ensure that a filler system used that reduces the risks of particulation. The common option for a filler is carbon black. Most of the black O-rings have carbon black in them, but carbon black leaves a powder residue at the surface when it's exposed to plasma, means that it causes particulation. But there are some other common fillers like metal oxide based, but again potentially not desirable for semiconductor applications, where metallic based filler can come out of the elastomer during erosion and can be dissociated in plasma and create metallic ion contamination on the wafer. And all of this still depends on how critical your process is to potential particle contamination, and those needs will be different if you are making, for example, a MEMS device or a 10 nanometer FinFET transistor. The particle requirement will be different. The type of the polymer used in the elastomer is one of the key factors determine the chemical inertness of the material. And most commonly used polymers in semiconductor industry are FKMs and FFKMs. And we always get questions from equipment users about what's the difference between FKMs and FFKMs. So in this presentation, in this slide, I'll try to explain the differences. FKM obviously being a fluoropolymer, and FFKM is a perfluoropolymer. Perfluoro means all the hydrogens on the molecular structure are replaced by a fluorine atom. And the examples of FFKMs would be Perlast, if it's a PPE material, Calres and Chemras from our competitors. A polymer is basically just a large molecular structure with lots of repeating units, which are called monomers. So you can see in both images, the repeating structures create a carbon-carbon chain surrounded with some other atoms. We also need a cross-linking site, and the cross-linking site is being used to join one polymer chain to another, which gives then the elastomer its rubber-like properties, the ability to be stretched or compressed through a force to create a sealing force, and then recover its original shape once the force is removed. So fundamentally, if we talk in generic terms at more of a top level, protection of a polymer backbone is the key thing to maintain the elastic properties of a material in aggressive environments. So let's have a look how the polymer backbones are protected in FKM and FFKM polymers. On the left hand side, you see a very basic FFKM chemical structure, consists of 3 different monomers, one being the cross-linking site, Now, our polymer backbone is the chain in the middle, consisting of carbon atoms. And on the right hand side, you see the most basic FKM chemical structure. It is, as you can see, very similar to the FFKM structure, but there is very slight difference. One is on FFKM structure, the carbon-carbon backbone is surrounded by mainly fluorine atoms. On FKM structure, there are again lots of fluorines, but we also have hydrogen atoms. So these make the difference. This is the only difference between them. And the part of the chemical inertness coming from various bond strengths. Now let's compare the strength of the bonds around the carbon-carbon backbone. In this table, on the left bottom side, you see the bond dissociation energies of the relevant chemical bonds. On this list, carbon-fluorine bond seems to be strongest bond, having 540 kilojoule per mole, and carbon-hydrogen bond seems to be weakest with 335 kilojoule per mole bond dissociation energies. So what does this mean? If an FKM material is exposed to a reactive substance, which can be a chemical, a gas, or plasma, the reactive species will attack to the weakest bond on the structure. So it will go to the carbon-hydrogen bond and break it quite easily. In simple words, breaking of these bonds mean that the backbone is also broken, and when the backbone of the polymer is broken, the elastic properties of the elastomer will be lost. On the other hand, the reactive species needs to be stronger to break the carbon-fluorine bond on FFKM structure, which means that FFKMs have a lot better chemical resistance than FKMs. I said the part of the chemical inertness comes from the bond strengths, and the other factor is the size of the atoms protecting the carbon-carbon backbone. Looking at the much simpler molecules like carbon tetrafluoride and methane, CF4 and CH4. In this case, CH4, the fluorine is a very big atom. In this case, CH4, the hydrogen is very smaller, a lot smaller atom than fluorine, which means that the shielding effect of hydrogen is a lot less than fluorine. So not only the bond strength of these chemical bonds, but also size of the atoms are the key factors protecting the polymer backbone from external reactive species. Okay, we talked about our main ingredient in an elastomer formulation. And now let's talk about the optional ingredient, which is the filler, which doesn't have to be in an elastomer formulation, but if there is one, it would be useful to know what kind of filler it is in the elastomer material. And in order to analyze the type of the filler, there are certain ways, but I will very quickly talk about the thermogrametric analysis, which is the short form of TGA, which is a very useful tool in our lab. It is actually basically a very simple device. It has a very sensitive balance sitting in a furnace, and we heat up the material up to 1000 degrees and monitor the weight loss, and the weight loss profile gives us very important information about the type of the filler. So in this specific example, you see the weight loss has started at around 450 degrees, which corresponds to the decomposition of a main polymer in the formulation. And then at like 500 degrees, you see a little bit of a small shoulder, which can correspond to a second type of a polymer in the formulation, which can be an organic filler, because organic fillers are usually fluoropolymers like PTFE or PFE type polymers, having more stiffness to provide a little bit more dimensional stability and plasma resistance to the elastomer material. So further increasing the temperature after 600 degrees, where we switch on the air instead of nitrogen, all the polymers, all the organics on the TGA pen decomposes, and we end up with a residue, and the amount of this residue is always giving us some tips about the amount of the inorganic fillers used in the formulation, because most of the inorganic fillers, they decompose at very high temperatures, like 2000 degrees Celsius, or even higher. So by looking at this profile, we can say if the material is organically filled or unfilled. Obviously, if there's no residue left, it is an unfilled, fully organic material, but it may have some organic fillers in the formulation. Choosing the right material for right semiconductor application can be extremely confusing and risky, and we help our customers to pick the right material for right application. But when specifying a sealing material, it is always an advantage for us to know some details, such as operating temperature, the expected lifetime, is it a plasma process, if it is, which gases, which chemistries, the type of the plasma, or what other chemicals can be used in the process, the type of a seal, is it dynamic or static, what's the pressure, etc. But more important than this, actually, it is very good for us to know what kind of end product will be made using this tool. It makes a great difference in the performance and the price of a material. For example, if a MEMS device will be produced in the tool, fully organic, extremely pure, therefore very expensive material do not need to be used. Traditional filled low-end semiconductor material will do the job. On the other hand, if a 7 nanometer FinFET device, for example, to be made, just the opposite, to avoid contamination and particulation, the purest possible material needs to be used for that location. Well, I'm sure a lot of you will know semiconductor manufacturing can be a bit of a risky business. As you know, chips are made on substrates or wafers, and there are many multiples of chips on each wafer, especially for larger wafer sizes. The capability to be able to process a lot of chips in parallel has obvious cost benefits. Fast output is always key requirement, and it needs to be fast to make maximum use of the expensive fab space and fab resources, all the equipments. Qualification of new elastomer sealing material is always a potentially high risk for semiconductor fabs and also for OEMs. When OEMs develop new semiconductor manufacturing tools, or when they improve their current ones, or when fabs think that their OEM qualified seal does not fit for their purpose, a new elastomer material has to be tested and qualified for the tool and for the application. For chip makers, finding the available tool time, running some dummy wafers, for OEMs doing the research and benchmarking tests of different sealing materials are always very risky. The risk can be the contamination of the chamber, or wasting staff and tool time for very bad performing material. At this point, PPE helps you to reduce the risk through doing a lot of tests by comparing the performances of the most common sealing materials in the market. So you will know roughly how the new material will perform in specific chemistries, comparing to some other well-known materials in the market, and then you will can easily make your decisions to start a qualification process or not. Now let's talk about a bit more in detail about plasma resistance of elastomer materials. Earlier in my presentation, I talked about the fillers and mentioned that if not used properly, fillers can cause contamination. Filler particles dispersed in the polymer matrix can become free upon plasma exposure as the polymer is etched away. You can see an image of an elastomer before it's been exposed to any chemistry, then again after exposure. Actually, it's pretty obvious which is which. So as I said, a bit of an extreme example, but we have seen that this material is very plasma resistant and tends to be amongst the best performing with very low erosion rates. But you can see the obvious downside, which is the potential to release very large micron size or even tens, even maybe hundreds of micron size particles into the chamber. Well, we have done a lot of plasma exposure tests. We have picked some of the most common chemistries used in semiconductor processes. We picked five different chemistries and different plasma sources, and exposed our and competitor O-rings directly to the plasma and measured the erosion rate. When we hear the word plasma in the world of elastomer manufacturing, it's often not appreciated that not every plasma is the same. For example, in PECVD process, the plasma configurations are generally capacitively coupled, where the electrodes are parallel to each other, and usually electrodes are driven by an RF power supply. However, in PECVD applications, for example, there are often chamber cleaning processes required, which use a microwave plasma source to generate very high radical to ion ratios, which can be more aggressive for an elastomer. You can see on this chart the weight loss values in percentages of tens of different elastomer O-ring materials, and high erosion rates or high mass loss is at the left of the chart, and low erosion rates at the right hand side of the chart. Low weight loss is obviously preferred, which means that the seals will last longer. However, as I mentioned earlier, low weight loss materials can be heavily filled and can release particles upon plasma exposure, which is definitely not wanted in semiconductor processes. The bars on the charts are color coded as to whether it's a PPE material, a development material from PPE, or from any other supplier. We expose all the O-rings directly to plasma and check the weight loss of each material. This chart is for direct oxygen plasma, which is mainly ion bombardment on the samples than the chemical attack. I'm going to show similar charts for weight loss tests in 4 other plasma chemistries. As you can see, the charts are quite simple, but there are a lot of data points. Therefore, I will highlight just some of them to emphasize the difference of the plasmas. So I highlighted 4 different materials on this chart, which are Kimura K13X and 3 of our development materials starting with GM codes. In this particular chemistry, which is direct oxygen plasma, the order of the highlighted materials are green, dark blue, red, and light blue. Now let's have a look at the weight losses of these materials in the same chemistry, actually another oxygen, but the type of plasma is different. It's remote oxygen plasma. Okay, before we forget, the order from the previous slide was green, dark blue, red, and light blue. Now we can see the order is blue, green, light blue, and red. So relative to each other, red and blue have switched positions, and green and blue have switched positions. And importantly, in terms of relative performance, there are some significant differences where a material that performed multiple times better than the other in the previous slide. Okay, looking at the process chemistry, the previous slide and this one are both oxygen. The only difference is the type of a plasma, previous one being parallel plate capacitively coupled plasma, we call it direct plasma, and this one is being a remote ICP plasma. Here we have similar data for chlorine-based chemistry. I haven't highlighted every material, but looking at this data, we can say most of the materials behave differently in different plasmas. Okay, this chart is for SF6 oxygen, high density remote ICP plasma. Again, I highlighted two materials. Both of them are being our current materials. One of them nanofluor Y75N and Kimura K13X. These two materials have moderate weight loss in SF6 oxygen ICP plasma. And now let's have a look how these materials will perform in just SF6 ICP plasma. Okay, let's have a look at the boxes first. And actually, it was a bit of a trick question. The order hasn't changed. It's still blue box and then the red box, but both of the materials have significantly shifted their position relative to those around them. So okay, this is slightly different chemistry, but both these materials were fairly good in SF6 plus oxygen, and they were pretty good in just oxygen environments. This again is about the manner in which the plasma is generated, and specifically the ratio of radicals created versus ions created. Whilst this is a different chemistry, the change in plasma source is a key factor, and understanding this is very important when it comes to recommending the correct material for us. In this case, we ideally would have wanted to do testing in a remote NF-free system. However, we had some difficulty in getting access to the hardware with this capability. In reality, however, the remote NF-free source is simply a good fluorine radical generator, and the data we have gathered in this particular test is consistent with other sources which have used remote NF-free plasma. So our material trends are similar to actual NF-free data. Okay, this is a summary of the plasma resistance charts. In order to simplify all the data, I have picked just a couple of grades which are quite popular in industry and compiled all the data on one chart. Now, I would like to talk about some of our new plasma-resistant materials. First of all, nanofluor Y75G appears to be very good, apart from the high radical fluorine type plasma environment. Nanofluor Y75G is a hybrid material, which is a mixture of FFKM and an FKM polymer. Therefore, as you can remember from my earlier slides, FKMs do not have very good chemical resistance compared to FFKMs. Therefore, this result is expected. This material has a nanoparticle filler system which has very high purity and relatively low levels of fillers. Okay, Perlast G67G. This material is very good in all plasma chemistries, including high radical fluorine plasma, as being an FFKM material. Perlast G67G has also similar type of high purity nanoparticle filler system to the previous material. And finally, I'd like to talk about Perlast G65HP. This material is an FFKM and quite different than the previous two. Perlast G65HB is a fully organic material. It means that it doesn't consist of any inorganic fillers in the formulation. It's fully organic. Even though comparing to the other fully organic materials on this chart, for example, Perlast G67P and competitor A1, its plasma resistance is way better than the other fully organic materials, especially in high radical fluorine plasmas. And Perlast G65HB is particularly recommended for chamber cleaning processes, very aggressive plasmas like NF-free remote plasma. Okay, some of you may say that Y75G and G67G materials are really good because they are heavily filled. On this slide, I put the thermogrametric analysis results of nanofluor Y75G and Perlast G67G against a very well-known competitor material. As you can see, nanofluor Y75G and Perlast G67G have 25 to 30% less filler amount than the competitor, which means that the chances of contamination of our materials are 25 to 30% less than the competitor. Okay, now you may ask, if there is less filler in our materials, how come the plasma resistance of these PPE materials are better? I already answered this earlier in the presentation, but I'll go through again. The filler particles protect the polymer matrix from the plasma attack, so they behave like a shield. So larger the surface area of the fillers, usually better the plasma resistance. The surface area of the fillers get larger by smaller the particle size to maximize the shield area. In our formulations, we use smaller filler particles, therefore we need less filler amount in our formulations to provide better plasma resistance than the competitor material. It sounds like very easy. By using the smaller particle sizes, we get better and better plasma resistance. So we can use very small particle size and have the best plasma resistance. But that's not that simple, unfortunately. As the particle size gets smaller, the processing of these fillers and dispersion in the polymer matrix becomes extremely difficult. As you may know, nanoparticles have very high surface energy, and they prefer creating agglomerates to reduce their energy, and very advanced polymer processing equipment and rubber compounding expertise is required to break these agglomerates and disperse in the polymer matrix to maximize the plasma resistance. Using scanning electron microscopy, we can now look into more detail of the structure of the compounds. As I said, nanoparticles are hard to disperse, and let's see how it was done in our competitor's material, competitor B2 coded material. As you can see from the SEM images, the dispersion is extremely poor. I highlighted some of the agglomerates, and even though the individual particle sizes are less than 100 nanometers, the size of the agglomerates are micron sizes, even some of them tens of microns. Therefore, we cannot really say this material is nanofilled anymore. And let's have a look how PP materials look like. If you compare previous material to nanofluor Y75G, the effect of the filler is significantly different. Firstly, the size of the filler particles are much smaller, at around half the size of previous material, and it's very noticeable that the filler particles are perfectly dispersed, uniform within the compound. I should also point out that the image on the right hand side is at a magnification of 100,000 times. The same applies to Perlast G67G. Again, comparing to the same competitor material, the dispersion is a lot better. Therefore, Perlast G67G provides better plasma resistance with a lot lower chance of contamination than the other material. Now, I have a special slide about Perlast G65HP. The plasma chart you see on the slide is the same as the last one. I'm just showing different competitor materials here. The competitor materials on the chart alongside Perlast G65HP are fully organic, except competitor A2, the blue one. As you can see from the chart, G65HP has better overall plasma resistance than the others, even though competitor A2 is filled with inorganic filler. The TGA curve on the bottom left shows that G65HP is totally organic. There's almost zero residue after the test. On the other hand, the competitor A2 leaves around 3% residue. Another important property of elastomer seals is the stickiness. Fully organic materials usually become very sticky when they are exposed to heat. I've been hearing engineers always complaining about the O-rings sticking in a groove when they want to replace. Some of them need to use some tools to remove the tacky O-rings from the groove, and they spend quite a lot of time. In some cases, they even damage the groove. So what we have done, we tested the sticking force of these three competitor materials and Perlast G65HP against stainless steel. We squeezed the O-rings between stainless steel discs and put them in the oven at 200 degrees Celsius for 6 hours and cooled down to room temperature. Then we measured the force to remove the plates from the O-rings. It can clearly be seen from the graph from the bar chart on the bottom right hand side. Perlast G65HP sticks a lot less, which means that it is a lot less stickier, which has potential to save some time and money for its users. I have explained the elastomer formulations and basically plasma resistance in my presentation so far. Now I'd like to talk a little bit more about the purity. In order to achieve better plasma resistance, using more and more filler in the formulation would be a big problem. What we are seeing now is that there's a trend that end users are becoming less tolerant to metal oxide type filler systems like titanium dioxide, and I assume it's not for to contaminate the device and effectively altering the switching characteristics or the electrical parameters of the device. In PPE, we are aware of this requirement, and we work very carefully to keep all the metal contaminants minimum in all of our material grades for semiconductor. First of all, we work very closely with our suppliers to have the base polymers and other ingredients with minimum metal content, and after that we perform all the process steps as summarized on the slide in clean rooms. The polymers and most of the other ingredients are made in the clean rooms, and we open those bags in our clean rooms and we do the compounding, extrusion, molding, and after molding the final parts we clean them and bag them up to high industry standards to keep the purity of the elastomers at the highest possible level. This table shows trace metal analysis of some of our materials, some of the competitor materials. This analysis technique is based on vapor phase decomposition inductively coupled mass spectroscopy, ICP-MS in short. It's very sensitive method, and we get an analysis of 30 metallic elements listed down to typically parts per billion level. If you look at the bottom line, to the total amount of trace metals, the best material seems to be consistently Perlast G67P, which has exceptional purity comparing to many other FFKM materials. Usually the filled materials have higher trace metal levels, like an example of competitor A5 and A1. And most of the OEMs, they have very strict trace metal requirements for critical applications, which is usually 10,000 parts per billion. Critical applications means where the elastomer part is in close proximity or in direct contact with the wafers, or directly exposed or immersed in the chemistry in the chambers. Our materials, nanofluor Y75G and Perlast G65HP, are being exceptionally pure within the critical OEM levels. G67G is also providing a very clean material. Okay, now we have come to the final slide. Let me summarize my presentation. Nothing really beats having some actual real data when it comes to choosing correct elastomer material for semiconductor processes. First of all, there's no magic material, one size fits all. all materials have different characteristics and different plasma chemistries. It is true that inorganic fillers tend to improve the chemical and plasma resistance of materials comparing to the fully organic materials, but excessive usage of fillers can cause some other issues like particulation or contamination. Precision polymer engineering provides new nanofilled materials, which are Perlast G67G and Nanofluor Y75G, which have very pure ingredients, have a minimum metal contamination, and provide a maximum plasma resistance, and therefore a longer seal lifetime and less cost of consumables for the users. Perlast G65HP, another new material of ours, has exceptionally good plasma resistance. It is fully organic material, which is ideal for very critical applications, for the smaller node sizes, for the future technologies. As PPE, our aim is to collaborate with our customers and suppliers to deliver the most technologically advanced elastomer materials for semiconductor applications. I would like to thank you very much for joining our webinar. So I think we may have some time allocated for any comments, or you may have some questions, or if you'd like to email me, you can see my contact details, and I will do my best to respond as quickly as possible. Thank you very, very much again, and now I think we can take some questions.
Okay, thanks, Murat, for your insight into the purity and plasma resistance of elastomer seals. Now let's get to the Q&A. We'll have about 10 minutes for questions, so feel free to type in your questions. And if we don't have time to get to your question, don't worry, we'll respond with an answer for you within about 24 hours. So here we go with the first question. How well does your data correlate to actual in-tool performance?
Okay, this is a good question, and so you ask how our information is related to the real world. Well, ideally, we want to replicate all the data in actual tool performance with our test results, and I can say that our data correlates very well with the in-tool performance. But we have done tests in 5 different chemistries, so it is sometimes hard to compare different recipes, but we have very good correlating data from our customers. Yeah, this data is quite good.
Okay, thanks, Murat. Our next question is, can you accurately predict the lifetime of the seals based on this information?
Okay, so can we say how long a seal would last based on our data? Well, this is a very tricky question, but the simple answer is no, because there are lots of different factors to consider when talking about the seal life. First of all, our tests are done by exposing 100% of the parts to the chemistry. There are no stress, no stretch, and also it depends on the location of the seal. The failure mechanism is also very important. We don't know if the failure mechanism is leakage of the vacuum or particulation. So it's quite hard to answer this question, but we cannot predict the lifetime of seal based on this data.
Okay, here we go. Here's another question. Can the type of filler change the chemical resistance of an elastomer?
Okay, the chemical resistance of the elastomer material is based on it's driven by the polymer. So as I said in my presentation, protecting the backbone of the elastomer is very important, and it is related to the chemical structure of the polymer. Fillers, in some cases, they reduce the surface area of the elastomer. Therefore, the exposed area to the chemicals of an elastomer material is reduced by adding fillers. So, in some cases, it may increase a little bit,
The inertness of the fillers are also very important. So the filler must be resistant to the media. For example, a filler pipe which is not resistant to fluorine radicals, for example, if it's used in the elastomer formulation, obviously the erosion rates will be higher. Therefore, it's not really affecting the chemical inertness of the elastomer material.
Okay, thanks, Murat. We only have time for maybe one or two more questions. So next question is, why don't you analyze silica in trace metal analysis?
Well, we don't know. Well, we have some other analysis done with silica, but silica is not in the OEM critical elements list, and this is trace metal data. Silicon is not a metal, therefore we do not list in our third metal trace metal analysis. But we do some tests of silicon, and we can share with who asked the question later on.
Okay, I think we'll have to wrap things up now. So thanks, Murat, for spending some time with us all today. To find out any more information about PPE's semiconductor sealing solutions, please visit the website, and as always, feel free to call or email any questions or queries. Again, thanks to everyone for taking the time to join us today and to learn more about elastomer seals and how PPE's solution-minded approach can help you achieve the results you need for your sealing applications. Thanks again, everyone, and have a great day.